In the example for section 2 of chapter 12, we found that the moment distribution process can be lengthy as we release each node one at a time multiple times. Under some circumstances, we can use modified stiffness factors to shorten the process. So in this problem, we'll use modified stiffness factors to simplify the analysis by moment distribution. And the key concepts we'll use are calculating stiffness factors considering support conditions and applying moment distribution to predict moments in a beam. And here's our structure. It's an indeterminate beam fixed at point A and roller supports at B and C. Moment of inertia and modulus of elasticity are constant along the length of the beam, and we're going to determine the reactions at the supports. To do that, we'll use the following approach. First, we'll approximate the answer. Because after we perform all the calculations for moment distribution and calculating the reactions, we're going to want to be able to evaluate the reasonableness of those results. And so let's use an approximate answer to help in that process. Then to begin the moment distribution analysis, we'll determine the stiffness of each member and the distribution factors. And we'll also need the fixed end forces. Then we're ready to apply moment distribution. Where we will clamp down all the nodes, release them one at a time, distribute the moment, reclamp it, calculate the carryover. Once we have performed that iterative process a sufficient number of times, we'll be ready to find the moments in the beam. Then we'll have sufficient information that we can use our equations of equilibrium to determine the support reactions. And to evaluate our results, we'll compare with the approximation. So let's begin by approximating the answer. For the vertical support reactions, let's assume that distributed load goes to the nearest vertical support. That means as we look at AY, BY, and CY, 2.5 meters worth of distributed load will go to A, 2.5 meters of distributed load will go to B from this direction, and although this is 1.25 meters and 1.25 meters, there's no distributed load here to contribute from that side. So we will expect AY to be approximately the 12 kilonewtons per meter times 2.5 meters, which will be 30 kilonewtons acting up. We'll expect BY to be 12 kilonewtons per meter times the 2.5 meters. There's nothing coming from the other side of B. This one we also expect to be approximately 30 kilonewtons up. And so CY we predict to be 0. But let's take a look at the elastic curve, the deflected shape we expect for this beam. It will start horizontal at the fixed support. It will be curved down underneath the distributed load, but then must curve back up. And in order for it to take this shape and still be supported at C, it must curve as so. Now to hold this shape, we would expect BY to be up, but we would expect CY to be down. So over here, we estimate it to be 0, but it will probably be down. But I wouldn't expect its magnitude to be nearly as large as the other two. Now the moment support reaction. As we look at the piece A to B, it's sort of like fixed at one end, roller at the other, with uniform distributed load, where we get a moment at the end. And we can find this situation inside the back cover of our text. And so fixed, roller, uniform distributed load has the moment of omega L squared over 8, but not clockwise. So we'll predict the moment reaction at A will be approximately minus omega L squared over 8, so a minus 12 kilonewtons per meter times 5 meters squared over 8 equals a minus 37.5 kilonewton meters, where clockwise would have been positive, because using moment distribution we're going to need to have one direction as positive, and we'll typically choose clockwise to be that direction. Now I'll point out this is our approximation. As we look at our elastic curve, our deflected shape, we see there will be moment at B. And since there will be, the moment at A probably won't be so large. So this is probably an upper limit. So now we have estimates of the reactions with some clues in terms of upper limits and relative magnitudes. Now step 2, the beginning of moment distribution. Let's find the stiffness and distribution factors. we'll begin by looking at bending stiffness. Now, since member AB, its ends are either fixed or continuous, the stiffness of the member is 4 EI over the length, and the length is 5 meters. And it's one stiffness for the member, but I'll draw both K's, or I'll write out both K's for each end just for our bookkeeping. But member BC has one end pinned, the other end continuous. We can use that to eliminate some of the work. In this case, the stiffness of the member can be taken as 3 EI over the length, which is 2.5 meters. And the carryover factor will be 0. Now the distribution factors. Since A is fixed, the distribution factor is 0. Everything that comes to that node stays in the support. Since C is pinned, distribution factor at C is 1. I'll point out, because we are using the modified stiffness, because one end is continuous and one end is pinned, we don't need the distribution for the pinned end. But we'll keep it there just for completeness of our note keeping. How about node B? Well, to find the distribution factor, first we need to sum all of the stiffnesses of the members meeting at node B, which means we need KBA and KBC. So we need 4 EI over 5 meters plus 3 EI over 2.5 meters. Find a common denominator of 5 meters, and this expression adds up to 10 EI over 5 meters. Now the distribution factor for BA would be KBA over the sum of all the stiffnesses at that node. So it's 4 EI over 5 meters divided by 10 EI over 5 meters. The 5 meters cancels, the EI's cancel, and we have a 0.4 is the portion of unbalanced moment that will come back into member BA. The distribution factor for BC is the stiffness of BC over the total stiffness at the node. So it's 3 EI over 2.5 meters divided by the 10 EI over 5 meters, and that evaluates out to be 0.6. Step 3 is to find the fixed end moments. We'll have fixed end moment at node A And notice that I'm drawing all of these clockwise to be consistent. I have fixed end moment at node B in member AB, and we'll have fixed end moment at node B for member BC, but not at node C because we're using the modified stiffness for this element. Now for member AB, this will be the fixed situation with uniform distributed load. And when we look inside the back cover, we see these are the fixed end moments in that case. Omega L squared over 12, but this one is not clockwise. So we have the fixed end moment AB is a minus omega L squared over 12, which is a minus 12 kilonewtons per meter times its length squared over 12, which is a minus 25 kilonewton meters, where we had considered positive to be clockwise. And the fixed end moment at the other end is a positive omega L squared over 12, which therefore is positive 25 kilonewton meters. It is clockwise. Now for member BC, fixed at one end, roller at the other, but there's no load applied, so we don't need to look that one up. This fixed end moment is 0. If there had been load applied somewhere along here, just remember that we need to use the fixed, roller supported diagrams from the inside back cover. Now for step 4, which is to apply moment distribution. Oop, there's a L in apply. Apply moment distribution. And so I've created a worksheet for our structure and for our calculations, a column for each joint or node and each member that meets at that node. So let's input the distribution factors we calculated. For node A, member AB, we found the distribution factor to be 0. And for node B, we found the distribution factors to be 0.4 and 0.6, and node C, 1. So we have 0, 0.4, 0.6, and 1, even though we won't use this one. And I'll use this extra line to separate between the distribution factors and the moments. Everything from here down will be moments, all of units, kilonewton meters. And so I'm not going to clutter up the worksheet by writing the units every time. I'm going to go ahead and leave those off. If we had been performing calculations where we're combining units, I would have gone ahead and written them out like you see me do in the rest of the example. For our fixed end moment, we found it to be negative 25 kilonewton meters at AB, positive 25 kilonewton meters at BA, and then 0 everywhere else. Negative 25, positive 25, 0, and this one we won't need because it's the pinned end. We're using modified stiffness for BC, and there'll be no carryover from the node B toward node C. So now we're ready to release a node. There's no need for me to release node A because the distribution factor is 0. Nothing ever comes back into this node, or comes back into member AB at this node, and then therefore there's no other carryover to the other end, etc. So let's release B. I need my unbalanced moment, and then I reverse the sign so I can distribute it. And at node B, we have a 25 plus 0, so we have negative 25 kilonewton meters that must be distributed according to these percentages. So I take my distribution factor 0.4 times the negative 25, and I get a negative 10 for the moment distributed back into member BA. I take the distribution factor 0.6 times the negative 25 kilonewton meters that I need to distribute, and I get a negative 15 distributed into member BC. And at this point, I'll draw a line underneath because node B is now in equilibrium. We'll clamp it back down. There is moment generated at the other end of member AB, not at the other end of member BC, but at the other end of member AB. Half carries over, and so we have a negative 5. We do not need to release node C because there is no moment. We do not need to release node B, it's in equilibrium, there's no unbalanced moment. We don't need to release node A because the distribution factor is 0. Everything that comes to this node stays in the support, none comes back into the member. So in this case, we only needed one iteration, and we are ready for step 5, which is to find the moments in the beam. And to do that, we'll sum up the moment in individual columns. So, at node A in member AB, we have a negative 25 minus 5. We get a negative 30 kilonewton meters. For node B in member BA, we have a positive 25 minus 10. So we have a positive 15 kilonewton meters. The other side of node B, in member BC, we have 0 minus 15. We have a minus 15 kilonewton meters. And remember, at node C, we had no fixed end moment because of the modified stiffness we were using and the fact that it's no load applied in member BC. And because of the modified stiffness, the pinned end at C, we never carry over moment into this node. So this one is 0. Now at node B, this summation should equal 0, and it does. So that's a good intermediate check. Now we have the information we need to find the reactions. We'll just use the equations of equilibrium to do so. Let's draw a free body diagram. Member AB, 5 meters long. There's unknown shear at node B, or just to the left of node B. There's the moment at the end, moment BA, which we found to be a positive 15 kilonewton meters. We have the uniform distributed load of 12 kilonewtons per meter, the unknown reaction AY, and the moment reaction at A, which we found to be a negative 30 kilonewton meters. So let's sum moments about point B, and I can choose whichever direction to be positive, clockwise or counterclockwise. I will choose clockwise since that's the sign convention we use for moments. I have positive direction but negative magnitude from the reaction at A. I have a positive contribution for the vertical reaction at A, acting through 5 meters, a negative contribution from the distributed load, acting over 5 meters, with its resultant at a distance of 5 over 2 meters from point B, and the moment at point B. We'll solve that for the vertical reaction at Y, and we get a positive 33 kilonewtons, so it is acting up. Now let's sum forces in the vertical direction. I'll choose up as positive. We have positive reaction at A, negative contribution from the distributed load acting over 5 meters, and a negative contribution from the shear just to the left of point B. We'll solve that for the shear just to the left of point B, and we get a negative 27 kilonewtons, and that's an internal shear, so it depends which side of the cut we're looking at, and so we will denote our positive by that symbol. Now, a free body diagram of member BC. This one's only 2.5 meters long, with an unknown vertical reaction at C, an unknown shear just to the right of B, and a moment at B that we found to be negative 15 kilonewton meters. So we'll start by summing moments about point B. Again, I will choose clockwise to be positive for my summation. I have positive direction but negative magnitude for the moment at B. I have a negative contribution from the reaction at C. I solve for the vertical reaction at C and get a negative 6 kilonewtons. So it is not up, but actually down. Then I'll sum forces in the vertical direction. I'll choose up as positive. I have the unknown shear just to the right of B, plus the negative reaction at C rather. The shear just to the right of B is a positive 6 kilonewtons based on our standard sign convention for positive shear. We still need to find the vertical reaction at B, and to do that I'll draw a free body diagram of an infinitely short piece cut out at B. So I have BY, the distributed load coming from the left acts over such an infinitely short distance it has no contribution. I have the shear just to the left of B, which I found to be negative 27 kilonewtons. The shear just to the right of B, which I found to be positive 6 kilonewtons. And I have moment BC and moment BA. Now notice I've drawn these counterclockwise. That's because of Newton's third law. the moments at the ends of the beam segments we draw clockwise. So for this tiny free body of just the node, it has to be equal and opposite, so they're counterclockwise. I could write in their values, but that's not relevant to the vertical equilibrium I want to apply. I will choose up to be positive, and so we have the negative 27 kilonewton shear on the left, positive reaction, minus the 6 kilonewton shear on the right. Solve that for By, and we get a positive 33 kilonewtons acting up. And now we're ready to evaluate our results by comparing them with our approximation. So we have found AY to be approximately 30 kilonewtons up, BY to be approximately 30 kilonewtons up, and CY we found to be approximately 0, but probably down. And again, we expect CY to probably be down and not 0, but not a very large number compared to the other reactions. The moment at A we found to be approximately negative 37.5 kilonewton meters, and we expect that's probably an upper limit. Now to summarize what we found from moment distribution. We found AY to be 33 kilonewtons up, BY to be 33 kilonewtons up, and CY to be minus 6 kilonewtons up, or in essence 6 kilonewtons down. And we found the moment reaction at A to be negative 30 kilonewton meters. So AY and BY agree fairly well. CY is not a significant portion of these, and it is negative, down, as we predicted. MA is close to our prediction, but this turns out to be an upper limit as we expected. So we'll conclude that we have reasonable prediction of the reactions. So now let's review the process we followed to obtain these results. We started by approximating the answer. We assumed that for vertical support reactions, the distributed load goes to the nearest vertical support. And then we sketched the anticipated elastic curve, that is deflected shape, and saw that our prediction for CY of 0 is probably not going to be true, that we expect actually a downward reaction, but its magnitude should be much smaller than AY and BY. We then approximated the beam segment AB to look like a condition that we have in the inside back cover of our text, and we recognize that because there is actually moment at point B due to the continuity, it will likely reduce the moment we see at A compared to the situation in the back cover of our text. And so we predicted moment to our prediction of approximate moment we recognize as probably an upper limit. We then found the bending stiffness for each member. Since member AB is fixed or continuous on both ends, we use 4EI over L for its stiffness. Since member BC is continuous on one end, pinned on the other, we use the modified stiffness of 3EI over L. And this is going to help reduce the amount of work we need to perform when we apply moment distribution iteratively. We then calculated the distribution factors and found the fixed end moments using information inside the back cover of our text. We then consolidated all of that information in a worksheet and then one by one released the nodes. But we did not need to release A or C, so we released B, carried over the moment, and found that we needed no other iterations. So we added up the information in each column and found the moments in the beam. We used those moments with free body diagrams of each beam segment, applied the equations of equilibrium, and found the reactions at A, B, and C. And then we compared those reactions obtained using moment distribution with the reactions we estimated or anticipated from approximate analysis. We compared them, found that our prediction for moment distribution is reasonable, and we're done. Good job.